So this we're going to talk about quicksort, which will be an example of an algorithm that will help us understand how randomized algorithms are developed, how they are analyzed, and this will also be an exercise for you in terms of learning how random variables work, how probability theory helps randomized algorithms, and so in that sense it's going to be a little exercise, and it's nice because having taken an algorithms course, you're probably already familiar with quicksort, the deterministic version. What we are going to do now is try to understand the randomized version. So, but let's remind ourselves what we are talking about. We are talking about the quicksort algorithm, and this was an algorithm invented in the 60s by Tony Hoare, and it's turned out to be extremely good, and its variants of quicksort are used extensively in a variety of contexts, but quicksort, the way it works doesn't necessarily give you very good asymptotic running time bounds if you expect it to be deterministic. We'll look at that more carefully, but for now let's remind ourselves how this algorithm works, and just to recall, we're talking about sorting, which means that the input is any array A of elements. Any array A of elements that can be compared. So, the easiest way to think about this, it's an array of integers, and you can, given two integers, compare. It could also easily work for comparison of strings if you want to compare it alphabetically, so on and so forth. So, all we want is that these elements be comparable, and for simplicity let's assume that these are distinct elements. This is not crucial requirement, can be easily done away with, but for simplicity we are going to assume that. And as you of course might know, the output is typically, let's even say that the algorithm, I mean the array A itself, but it should be rearranged so that it's in sorted order. So, this is the requirements for any sorting algorithm, and let's think about a few things, or recall a few things that we already know about sorting algorithms. One is we are focusing on comparison based sorting. So, a fundamental bound that we have to respect is that the worst any sorting algorithm is going to require of n log n time, and here n is the number of elements. So, you can so there is no hope of getting an algorithm that's going to run faster than n log n. So, in other words, an algorithm that runs in little o of n log n in this context simply does not exist. Okay. So, we know that, and so we have to live by this bound. So, let's look at how quicksort works. Quicksort works in, you can think of it as working in 3 steps, but there's actually a recursion involved. So, at a high level, you consider the full array. Okay, this is your array A. The first step is pick a pivot. Okay. well, this is our array A. Let's pick a pivot element, and without loss of generality for now, we're going to pick the first element. Let's say this is the pivot element. Okay. And then the second step would be rearrange the array A such that elements that are less than the pivot, and let's call this pivot P, okay, rearrange this array so that elements that are less than the pivot come to the left of the pivot. So this anything that's, or let's say less than or equal to P gets placed to the left of the pivot, and then you place the pivot P. So this now. So now we're rearranging the array, and then all elements that are greater than P are placed to the right of the pivot. Okay. And now after this rearrangement, we can split the array into two subarrays. This is subarray number 1, and this is subarray number 2. Okay. And all we have to do now is recursively apply this algorithm on the two subarrays. Okay. So this provides us with a way to sort the algorithm, and it's an easy exercise to see that this algorithm is going to be sorted. And so that will be left as an exercise for you to prove that this algorithm works. And so let's now think about how good this algorithm is. Notice that this algorithm works by this divide and conquer paradigm. Okay. Each time the problem, the input is this array A. As when we recurse, we are working on a smaller part of the array, and each time you recurse, the problem size gets broken into a smaller piece, and then we know how to put the solutions together and build the solution and build the final sorted array. So this divide and conquer can go wrong. So how could this go wrong? If you are not familiar with this, now might be a good point in time to pause and just think about why this algorithm could go not wrong, but could operate very slowly. Think about what could happen. So pause for a little while and come back if you need to. Okay. Now let's just to complete the story, let's see what could go wrong. So we chose the pivot to always be the first element in the array. Okay. If the array is already sorted, what is going to happen every time you choose the pivot, there's going to be no element to the left of this pivot. All the elements are going to be there to the right, which means that the one side of the problem will be of size 0, the other side the problem will be of size n minus 1. So yes, the problem size reduces, but the problem size does not reduce significantly. So this will roughly correspond to well, the first instance you're dealing with n you will spend about theta of n, or let's just approximate it to n time steps to rearrange this array in the first recursion. In the next one, it'll be your problem size wouldn't have reduced much less than that. It would have become n minus 1, n minus 2, and so on up to 1. Okay. And this will add up to something that is theta squared. So this unfortunately does not give us good running time. In particular, it's far away from what is potentially achievable. Okay. We know that n log n is a lower bound, but we're getting a worst case running time of theta of n squared, and that's under this form of input. And so that's something that we would like to fix. We would like to understand this quicksort algorithm, maybe make a few modifications to achieve our goal, which is n log n. Okay. But there is unfortunately no hope of doing that with as long as we insist on a deterministic choice of the pivot. Okay. So that's again a good exercise. For any deterministic choice of pivot, can you design an input array sequence so that the worst case, the running time will be theta of n squared. Now that's a good exercise for you as well, so think about that. But much of this bad situation occurs because the input has a specific form and the algorithm does something very specific, deterministic to be precise, and that just doesn't work out well for us. How do we break out of this bad situation? And that's where it would help for us to look at this from a randomized perspective. Okay. So now we'll have to think about how to apply randomization. There are a few ways to think about it. Let me point out one way to think, point them out. One, let's assume that one way to bring in randomization is to assume that the input is a random permutation. If we want to be a little bit more pedantic, we can add uniformly random permutation. What this means is that given n items, there are n factorial possible permutations, and among those n factorial possible permutations, we have chosen one uniformly at random. So each permutation occurs with probability 1 over n factorial. Okay, and if this is the case, then let's intuitively think about what happens when we apply this simple quicksort algorithm. Well, when the first pivot is chosen, it's going to be very low probability that it will be the one pivot that does a really bad job of splitting the problem size into two subproblems. So the pivot is likely to be somewhere in the middle, and if the pivot is likely to be somewhere in the middle, then the two subproblems that we will get will be of roughly equal size. Okay, and that is significantly helpful. Let's reason that out a little bit more carefully. So let's somehow, to get our feet wet, assume magically that the pivot is exactly the median, okay, each time. If somehow magically the pivot always ends up being the median element in the subarray that is being worked on, then the running time is given by the following recurrence. Let's say T of n is the running time when the problem sizes of is n. The nice thing is, since you are going to use the median to split the problem, you're going to get two subproblems. Each one of them is going to be no more than the ceiling of n by 2. Plus, you'll have to spend some time arranging them, the smaller elements to the left of the pivot, larger elements to the right of pivot, and so on. So that's going to be theta of n. Okay. And this, we know, is, well, another exercise for you. Is going to be theta of n log n. Okay, if you can do this perfectly. Of course, this is hinging on a very unlikely if, and this only works if the pivot is always the median element, and that's not going to happen. But the intuition is very important, because now when we come back to this random permutation, the intuition is even this intuition is actually quite strong. It doesn't even have to be exactly splitting the problem into half. It could even, for example, this n log n would work even if the problem gets split into some fraction. So let's say the problem gets split into some alpha n, where let's say alpha is a constant between 0 and 1 open interval, and alpha is a constant. It must be a constant. And if you think about this, what this means is that the split need not be perfect, but it has to be a fractional split. So even if you can ensure that the pivot is somewhere in the middle, somewhere between, say, the 10th percentile and the 90th percentile, that's also fine, because then the two problem sizes, the larger of the two problems, will not exceed a 90%. That will correspond to alpha equal to 0.9. Okay, as long as alpha is a fixed constant within this open interval, we are fine. Okay, we will still be able to get theta of n log n. Okay, so that gives us a lot of hope, because this, when we use randomization, we're likely to get the element, the pivot element, to be somewhere in the middle. Okay, so that gives us a hope that this will work, and it's in fact correct. But the problem with this is you cannot always assume that the input is going to be uniformly at random, because the context, the application context, could mean that you're sorting an array that's almost sorted already. You're just correcting the few places where it's not sorted, in which case this algorithm is going to be, I mean, you cannot make that assumption that the input is uniformly at random. So there's a small fix to it. So the fix is the following. You don't make the assumption that the input is uniformly at random. You do that pre-processing step. In other words, shuffle it. Okay. Here's another small assignment for you. Think of a way to shuffle n items so that the output is a random permutation of those n items. So that's a nice little homework for you as well. So if you can shuffle it, even if the actual input is a bad input, for example, even if the actual input is already sorted, when you shuffle it, you're going to essentially mimic input being uniformly at random. Okay, so that's a possibility. But this will require you to have written a pre-processing step. So let's see if we can avoid that. So the third possibility is that that you actually do the randomization within the algorithm. So the algorithm is no longer going to pick the pivot as the first element in the array. Neither is it going to pick the element always as the last element or any deterministic way. Instead, what it's going to do is it's going to consider all the n items in the array and choose a pivot uniformly at random. And then when you get to the sub-problem, well, these are your options for the potential pivots. You choose one uniformly at random. At each recursive step, you choose a pivot uniformly at random. That's randomization within the algorithm. Okay. So essentially, if you think about it, all of these three options are essentially equivalent. Okay? It might take a little bit of effort to figure out that this 3 is also essentially equivalent to the other two options, but I'll let you think about it at your own time. So what we're going to focus on now is to take this option 3 and analyze it and show that it actually has a running time that matches this n log n lower bound. But keep in mind that when you randomize the algorithm, the running time is no longer a deterministic quantity. The running time is a random variable. and so that's something to keep in mind. So you cannot really say give a direct bound on the running time, but rather what we're going to focus on is the expectation of this running time. We're going to give a bound not on the running time directly, but the expectation of the running time. Okay. So let's see how we can arrive at that. Okay, so yes. Yes.
So could you please explain me the contribution of theta of n in the running time of this algorithm?
Okay. Okay, so the question that's being asked is the contribution of theta of n within the running time. So presume this is what you're asking about, T of n equal to let's just approximate it to n by 2 plus theta of n. And I presume your concern is this theta of n, how this is arrived. Okay, let's recall the algorithm. Pick a pivot, and the second step, this is where it matters. Array, and if you recall, we rearrange the array so that the elements to the smaller than the pivot are to the left, elements that are larger to the pivot are to the right. So how will that happen? So once you have the array, what you have to do is put all the elements to the that are smaller than the pivot first into the array. Well, this is one way to do it. Let me give you the simplest way that I can think of. Put all run through the list of elements in the array. You can think of this, for simplicity, you can think of this as another array B, in which you put all the elements that are smaller than the array, smaller than the pivot first. So you start filling in the array, but you're going through the entire list in array A to fill in this array B. Okay. Once you've exhausted the array A, these are all the items that are smaller than or equal to P, and then you put the pivot. Okay. Then again, whatever is left, whatever has not already been used over here, you're going to fill it up over here. Okay. This step of rearranging the items and putting them into this array B is what gives you this theta of n. You have to go through the entire list of array elements to be able to create this array B. Okay. And there are some fancy things you can do to simplify it, but this is the idea. Okay. All right. So now coming back to the randomized algorithm, think about how we chose the pivot. We chose it deterministically in the earlier case. We're going to pick the pivot uniformly at random. Okay, and then we're going to rearrange the array, and then third step will be to recurse. Okay. So now the operation of this algorithm can be thought of in this following manner, in this sort of divide and conquer tree. The problem size to begin with is n, and then choose a pivot uniformly at random. Then whatever happens to be on the left side of the pivot becomes the left subproblem. Whatever happens to be on the right side of the pivot happens to be the right subproblem. And then again, now for each of these subproblems you recurse, which means you again have to choose a pivot. This basically, this node here in this tree corresponds to a subarray. Okay, and you further subdivide and divide and conquer, and so on. Okay, and so on. Okay, so, and we want to get a handle on the running time of this algorithm. And as you may be aware, in a lot of sorting algorithms, we don't really compute the actual running time, but we rather compute the number of comparisons. So we're going to be concerned about the number of comparisons. Okay. So we're going to approximate the running time by the number of comparisons, which means that we need to think about a way to break down our understanding of the total number of comparisons into smaller pieces that we can handle, and then we can put them together. So if you're wondering how this will work, this is where the notion of linearity of expectation will come into play. So let's think through this a bit carefully. Okay. So what we're going to do now, remember our input array is this array A. Okay. For the purpose of analysis, let's consider the array, let's call it Y. Okay. Y is nothing but the sorted view of A. Basically, array A that is already sorted. Okay. Obviously, if you know the array Y, you can just output that. So you don't know array Y, but what we're going to do is just analysis. For the purpose of analysis, we're going to look at array Y. So Y comprises Y1, Y2, Yi, Y. Okay. And these are all sorted. So we know therefore Yi is less than or equal to Yj. And now what we're, and this is the sorted view, and okay, so let's assume that they're all distinct elements. So Yi must be therefore strictly less than Yj. In order to get a handle on the total running time, let's define a very simple random variable corresponding to these two elements Yi and Yj. We're going to call that random variable Xij. Okay. And this Xij can take one of two values. It can be either a 1 or a 0. It's a 1 if Yi and Yj are compared by the algorithm. And because of randomization, there is no guarantee that Yi and Yj will be compared. They may be compared, they may not be compared. Okay. So if it's compared, then Xij is going to take the value 1. If it's not compared, Xij is going to take the value 0. Okay. 0 otherwise. Okay. And if you think about it, this algorithm is only going to compare two items at most once. So if you want a handle on the total number of comparisons, let's denote that by the random variable x. That's essentially equal to this double summation. Okay. This is essentially the easiest way to think about it. For the moment, ignore these two summations. This is Xij. It's just it's going to be a 1 when Yi and Yj are compared. But then that's just one comparison. You have to account for every possible comparison. And how do we do that? Well, that's where this double summation comes in. I runs from 1 to n minus 1. And the moment you fix an I, you don't want to compare. You don't want to consider a j that's prior to I. You want to consider, because you want every unique pairing. So we want to consider j values that are larger than I. So once I is fixed, j runs from I plus 1 all the way to n. Okay. And with these two summations taken over Xij's, we will get every possible Ij combination with I not being equal to j. Okay. Do you have a question? Yes, please.
So actually, you said about this comparison between Yi and Yj.
Right.
Is it like any one of them will be a randomly selected pivot?
We have to discuss that. Your question is a natural lead-in, because now when we consider the values that when xij will be 1 and when xij will be 0, that will depend on whether yi or yj were chosen as pivots. Okay? Right now yi and yj are just two elements within this sorted view. Okay? So the question therefore is, what values can xij take? And it's 1 or 0, but when will it take the value 1? Okay? That's the question. Okay? So go back to this picture where we show the recursion. So let's fix an I and j. So this I and this j is fixed. We want to know when these two elements are going to be compared, because when these two elements are compared, xij value is going to be a 1. Okay? So initially I and j are both inside the same array that is being considered. Okay? And maybe they will continue to be in the same subarray. So maybe they both go into the right subarray here. Okay? Eventually, this at the end, it's only going to be singleton elements in the leaf. So at some point, the I and j will have to split. So let's say, without loss of generality, that I goes to the left here and j goes to the right here. Okay? So something happened over here in this subproblem that split the I and the j. The yi went to the left subproblem and yj went to the right subproblem. What happened? Why did that split happen? Well, it happened because a pivot was chosen, and that pivot has a value that is somewhere between yi and yj. Okay? This is when a pivot of this form was chosen, that pivot was compared with yi and it was put on the left subproblem, and pivot was compared with yj and yj was put in the right subproblem. Okay? And that's why I and j got split into the two subproblems. Okay? And if let's consider the case where the pivot was strictly between yi and yj and not neither yi nor yj. Okay? If that is the case, up until this point in time, the pivot is always fully to the left of yi or fully to the right of yj, which means that yi and yj themselves were never compared. And even at this point when they were split, since the pivot is fully between y and in particular neither yi nor yj, yi was never really compared with yj. Yi was compared with the pivot and yj was compared with the pivot, but these two were not compared. Okay? So every time the pivot is chosen in the middle, excluding the two yi and yj's, then no comparison takes place. The only way a comparison can take place is if either yi is p or yj is the pivot. Okay? These are the only two possibilities under which these two elements yi and yj can be compared. And what is the probability of that happening? Well, how many elements are there between yi and yj? Well, so in this picture, if you think about it, is yi plus 1 and so on up to yj. So there's going to be j minus I plus 1 possible elements in that range. Out of them, there are two elements, if chosen as the pivot, will imply that yi and I mean if the pivot is chosen either as yi or yj, then the two elements will be compared. So the two possibilities under which they will be compared. Okay? So this is the probability with which xij is equal to 1, and it's going to be 0 otherwise. So we can write that up here. Okay, And if you think about this, this is also the expected value of xij, because xij can be 1 with this probability and with probability 0 with the remaining probability. So the expected value of this random variable xij will be nothing but 2 over j minus I plus 1. And just a little intuition, if the two elements yi and yj are far apart, the denominator is going to be large, in which case the probability that they will be compared is small. If they are close to each other, then that probability increases. So that you should think about why that's the case, and you should think about how that has a bearing on the rest of the argument. Okay, so now we know the expectation of this xij. What we really want is the expectation of this random variable x, which captures the total number of comparisons. Okay, we want E of x. Okay, that's the expectation, which is E of this whole quantity. Okay, and the nice thing is, when it's expectations, you can apply expectations over the sum of a number of random variables. You can apply the linearity of expectation, so you can simply take the expectation inside. We can write it this way. Okay, and if we can write it this way, and we already know a formula for this, so let's try to simplify this whole thing. Now, E of one, two, and I'm going to actually substitute the value here. Remember, E of xij is 2 over j minus I plus 1. Okay, and that's equal. Let's simplify things a little bit. So let me be a bit sloppy here. 2, and here I'm going to run I equal to 1 all the way to n. Now this will only increase the quantity on the right hand side, but I don't care about it. I want an upper bound on the expected running time. Okay, so then let's see what we're going to do here is, okay, so now I'm going to use a different variable for iteration here. I'm going to let this run. Let's see, what is the smallest value that this denominator can take? Okay, this denominator can take, the smallest value it can take is 2, because j is definitely larger than 1 by at least 1. So this quantity is at least a 1 plus a 1. Okay, so this summation will, if you think of the denominator, it will be 2, then it will be 3, 4, and so on. And the largest the denominator value can be is when j equals n, in which case the denominator will be n minus I plus 1. Okay, so the denominator will run from 2 to n minus I plus 1. Okay, so we're going to simplify that. So we're going to run the denominator from 2 to n minus I plus 1 and write it as 1 by k. Okay, and simplify this further. So this is running up to n minus I plus 1. I'm just going to make it run all the way up to n. Okay, well, and I even, let's say I start it at k equal to 1. Okay, remember, all this I can do because I'm looking for an upper bound, and I'm being a bit sloppy here, but to make the analysis simpler. So this quantity is nothing but the nth harmonic number. Okay, this is denoted Hn, and this is equal to ln n plus theta of 1. This is a known quantity. And so essentially this is O of log n. Okay, and this, what is within this box, is an O of log n quantity, and we are summing it n times times 2. Okay, so as a result, this whole quantity, this whole quantity belongs to theta of n log n. And this is, oh, by the way, theta of, so this whole quantity is now theta of n log n. So what we have been able to show here is that the expected number of comparisons, which is the surrogate for the running time, the expected number of comparisons is at most theta of n log n. This is so what this tells us is that on expectation, randomized quicksort is going to have a running time that is of the order of n log n. Okay. There still can be bad cases. There could be times when the algorithm runs a lot slower than that, but it's going to actually be rare. So in a subsequent lecture, when we talk about Chernoff bounds, we will look at the same quicksort. We'll actually try to prove that quicksort is not just good on expectation, but it's actually good with high probability. We're going to actually be able to say something stronger about this random variable. We're still going to focus on this particular random variable, but what we're going to be able to say is that this random variable x will be of the order of n log n with high probability, with overwhelmingly high probability. Okay, but that will require a little bit of knowledge on some other probability theory tools that we will look at in a subsequent lecture. So any questions? No questions? Okay, so we're done. Thanks.